Welcome. As folks are joining, let's just give us just another minute or so, and we'll allow everyone to join in. We'll get started. We thank you from wherever you're joining us from. And I've seen some attendees are coming from Asia, so late in the evening for them, but we appreciate your participation today. And again, while we're waiting for folks to join us, just want to thank any of you who were with us in Providence a few weeks ago. We had an excellent conference. The Cable and Connectivity Industry Forum really had some outstanding presentations like the one you're going to be seeing today, but also some really intriguing panel sessions, and our plenary keynote was outstanding. So we hope that we can build on that for next year, and that you'll participate with us. Okay, well, let's go ahead and get started. Again, greetings, good morning, good afternoon, good evening, and late into the evening from wherever you're joining us from. My name is Dave Cadu. I'm the CEO and Director of IWCS, and I'll be your moderator today. A few housekeeping items. As a attendee, you're part of a larger audience. So during the presentation, all participants will be in listen-only mode. And also, as a reminder, this webinar is being recorded for rebroadcast. It'll be available on our YouTube channel and from our website as well, if you or colleagues want to watch it at a later date. You'll also find there all of our previous webinar recordings as well, if you want to scroll through and see some really fascinating papers. We encourage you to submit questions in the chat function during the presentation. The chat panel will be on the right of your screen. So type in the questions that you have in the space at the bottom, and be sure to hit the send button. And we'll be monitoring that, and your questions will be addressed, time permitting, at the end of the presentation. Today, we welcome Vincenzo Alton Popiolik. He is a recent graduate from Virginia Tech, and he will be presenting today on sustainable options in polyethylene cable jacket materials. Vincenzo graduated in May of this year, and with a bachelor's degree in materials science and engineering from Virginia Polytechnic Institute and State University. And he joined Volvo Trucks in August of this year as an associate engineer. So again, we welcome Vincenzo to present today's topic on sustainable options for polyethylene cable jacket materials. Thank you.
Yeah, thank you so much for having me. My name is Vincenzo Alton Popiolik, and today I'll be presenting to you on sustainable options in polyethylene jackets for optical fiber cables. This research was conducted by myself, as well as two of my fellow colleagues, Jordan McCreary and Cole Klabowski, in the Materials Science and Engineering Department at Virginia Tech. This was done under industry advisor, Dr. Brian Risch with the Prysmian Group, and faculty advisor, Dr. Gary Pickrell. Slide switching, sorry. So a little on our motivations and background. So as the world continues to struggle with increased greenhouse gas emissions and waste, the Prysmian Group has committed itself to its environmental responsibility. In this study, we'll be focusing primarily on the circular economy and waste aspects of these commitments. We'll do so by considering the composition and source of their cable jacket materials, looking for more sustainable options. The Prysmian Group has split their circularity targets into 4 different classifications: reducing waste at its source, reusing material, recycling waste, and purchasing more recycled materials. As such, the use of circular raw materials has become a key sustainability objective, as it allows for the using of fewer natural resources and keeps the materials within the production cycle for as long as possible. The most common material currently used for these outer cable jackets is polyethylene. Polyethylene used in the wire and cable industries accounts for about 2% of global polyethylene consumption of about 160 million tons. Polyethylene production is continuing to increase, and plastic waste continues to be recycled at a very low rate of only about 8%. One benefit of working with polyethylene is that it can be mechanically recycled, which is as in the figure on the left, it is ground up and then reprocessed so that it can be reused. In this study, we'll focus specifically on post-consumer recycled, or PCR polyethylene, which is polyethylene that has been used before commercially by users and is then mechanically recycled. Again, emphasizing circularity as it is able to go through its full life cycle before then being reused. On the left here, we see a fiber optic cable with its many different layers. We will be looking at this outer orange layer, in this case, the outer jacket. By changing to a polyethylene jacketing compound with a more sustainable source, we can make a dramatic improvement on product circularity and help reduce overall environmental impact. In order to achieve this, our overall goal was to create a final blend of virgin and PCR material that maximizes the PCR content while still passing industry standards. This was split into 3 different sets of objectives. First, during initial characterization, we performed baseline testing on all of the locally sourced polymer samples. The locally sourced aspect of this project was very important, as while the Prysmian Group has already had success with this project overseas in different countries, the need to ship these back to the United States would cut into the sustainability of these blends due to the increased greenhouse gas emissions. Next, we also retested all of these polymers after thermal aging. This was in order to check for the durability of these sustainable blends, as they need to be able to undergo a similar life cycle as their virgin counterparts, as if they have to be replaced more frequently, that would again cut into their sustainability. Finally, we also characterized PCR polymers to quantify their variability. One issue when working with PCR polymers is that it often comes from various different feed streams. Some may come from a single-use application, while others may have been exposed to environmental conditions for long periods of time. As such, we see far greater variation than compared to their virgin counterparts. As such, this is something that needs to be designed around and considered. Next, for thermal aging, during initial characterization, we aged our samples in a furnace at 100 degrees Celsius for 60 days. This was to simulate a 50-year life cycle out in industry. For our final blends, we then aged these for 14 days. This shortening of time from 60 days to 14 days was due to time constraints. However, that is still twice the industry standard of 7 days. Finally then, for blending, we aimed to fabricate blends which passed industry standards, and then test the blends to ensure they perform comparable to the benchmarks provided to us. For experimental procedure, we performed a variety of tests to compare our polymers and blends to industry standards. A few key tests are highlighted here. We performed oxidative induction time, or OIT, to test for resistance to oxidation. Thermogravimetric analysis, or TGA, to test for thermostability, contamination, and carbon black content. For thermal stability, we specifically checked to ensure that no degradation was seen under 100 degrees Celsius to ensure that this was an appropriate aging temperature for our thermal aging. We ran melt flow indexing to check for viscosity, tensile testing for yield stress and elongation at break, specific gravity for density, and environmental stress crack resistance, or ESCR, for resistance to degradation under corrosive conditions. For those of you not familiar with ESCR, what we do is we mold a plaque out of the polymer. From this, we then punch out tabs. These tabs are then nicked with a nicking jig to induce a stress concentration. These are then bent along the stress concentration and added to a metal grid, which keeps them in that stressed position. This metal grid is then added to our corrosive conditions, which in our case was a slightly basic solution. The corresponding ASTM standards are listed on the right. Our industry standards are provided to us by the Insulated Cable Engineers Association. There are different requirements for each different density of polyethylene. The MDPE requirements are highlighted here as that was the target density for our final sustainable blends. In order to be considered MDPE, the density of the polymers must lie between 0.94 and 0.955 grams per centimeter cubed. The ultimate elongation must reach at least 400% and retain at least 75% of its original performance after aging for 7 days. The yield strength must be a minimum of 8.3 megapascals, and similarly retain at least 75% of its original performance after aging. OIT must reach 20 minutes, and ESCR is allotted 1 failure out of the 10 samples after 48 hours for a type B specimen. One thing to note for ESCR is there's 2 different types of specimens. Type A, which is slightly thicker and a slightly more strenuous test, and type B, which is slightly thinner. The type A specimens are typically used for lower modulus polymers, such as linear low density polyethylene, while the type B specimen is used for higher modulus polymers, such as MDPE and HDPE. Carbon black content was targeted at 2.5%, plus or minus 0.5%. The Prysmian group provided us with 11 different compounds of varying PCR content and density, which were tested and evaluated for use in our blends. We were provided with 3 virgin polymers, a high density, medium density, and linear low density polyethylene. These are polymers currently used by the Prysmian group on the lines and will serve as our controls, but can also be used for blending for our final sustainable blend. We were then also provided with 3 benchmark PCR blends. These are blends which are already used in the telecom cable industry and range in PCR content from 30 to 45%. These are the polymers which we will aim to mimic the performance of while retaining a similar or higher PCR content. Finally, we also received 5 high PCR content blends ranging from 70 to 100% PCR, which would be hopefully used to create our final sustainable blends. Due to information security purposes, we were not able to provide the generic names for the polymers which we tested for this study. So instead, we designed a naming convention which will be used to reference these polymers throughout the rest of this presentation. This consists of the first 2 letters of the density, so HD for high density, MD for medium density, and LLD for linear low density, followed by the percent recycled content, and finally a 1 or a 2 to distinguish between 2 blends which have the same density and PCR percentage. Moving on to our initial characterization results, we classified our results in 3 categories: red for failing, if they're failing industry standards; yellow to flag a value, meaning that there wasn't necessarily an industry standard, but the values were removed from what we were looking for; and then white for passing. For our virgin polymers, as expected, these passed industry standards across the board and far exceeded them. Again, this is expected. These polymers are currently already used by the Prysmian group and will serve as our controls. Next, for the PCR benchmark blends, these also, as expected, passed industry standards. These are also already used in the telecom cable industry, so again, we expected them to pass. But these are the properties that we are aiming to mimic with our final sustainable blends while having a similar or higher PCR content. Finally, for the high PCR content blends, as expected, this is where we saw our failures and our issues that we'll have to try to compensate for in blending. First of note, the linear low density 100 sample, we see that there's a lot of asterisks. So for the asterisks for melt flow index, while there is no industry standard for melt flow index, it was still deemed a failure, as rather than flowing through the die during testing, the polymer actually flowed around the die. So this was deemed to be unusable on the Prysmian group's lines, and as thus was not subjected to further testing, noted by the double asterisks in the other categories. Looking at our other 4 remaining blends, for OIT, which has an industry standard of 20 minutes, we see that all of the different blends failed. However, this was not of great concern to us, as OIT is the easiest property to improve through the use of antioxidants. And as such, we didn't feel the need to design around too much, but it was good to know that we needed to add antioxidants. For ESCR, which has an industry standard of 48 hours, we see that the linear low density polymers were able to significantly surpass industry standards, reaching over 1,000 hours, while the high density samples both failed at only 24 hours. We believe, however, that this was due to the high modulus which we saw in the high density polymers, and that by blending with a lower modulus polymer, we would still be able to consider these for blending and be able to surpass that 48-hour threshold. Further, it should be noted, all of our initial characterization testing was done on the type A, more strenuous ESCR tabs. And as such, we do believe that the HD samples may have passed if they're subjected to the less strenuous type B, which is what they're expected to be tested against. For yield stress, we see that all the polymers were able to pass industry standards. For elongation percentage, which has an industry standard of 400%, we see that the linear low density polymers, again, were able to pass industry standards, while the high density polymers both failed. However, of note, the HD101 failed at only 15%, having quite a brittle failure, and this was not something that we thought that we could compensate for in blending, and as such was not considered for use. While the HD102 reached 307% elongation, which was much closer to the 400% threshold, and we were hopeful that by blending with a higher ductility polymer, we would be able to surpass that level. For melt flow indexing, there is no industry standard. However, our target was for our final sustainable blends to have a melt flow similar to the virgin polymers currently used by the Prysmian group to make for easier processing. As such, the linear low density polymers were flat as they were furthest removed from those virgin polymers, while the high density polymers were deemed close enough to be an easy transition. We also quantified the variability of the PCR in order to emphasize this variation. As we move down and in increasing PCR content, we see that the variation increases significantly. The numbers here represent the standard deviation as a percentage of the actual value. And as such, we see that in the virgin and in the benchmark polymers, we have variations ranging between 1 and 15%. So quite low and within a usable range. While as we go to 70 to 100% PCR, we see those ranges increase up to 65% for some categories, which is much harder to use and borderline unusable. And that is something that we had to consider when blending. But we did hope that by blending with lower variation polymers, we would be able to decrease that variability in our final blend. From this, we were able to develop our blend criteria. So of highest importance, we deemed processability, as the Prysmian group needs to be able to run these polymers and these blends on their lines, maintaining a similar throughput without having to change the conditions on their lines too drastically. Next was environmental stress cracking, as this is one of the more common failure mechanisms seen in the field and something that is harder to change as there are no additives you can add to improve this, and thus is something that needs to be designed for more actively. Of secondary priority was PCR content, as while we wanted to increase this as much as possible, we had to make sure that we were still passing industry standards. Then tensile strength and percent elongation. While we still need to pass industry standards for these, it is not as common of a failure mechanism, and as such we did not feel a need to optimize much past that level. And then finally, for our tertiary priority was oxidative induction time, as this is something that is the easiest to change, as we can add an antioxidant package and thus did not need to design around this. Finally, using these criteria in our initial characterization results, we were able to create a 50% PCR blend along with a 45% and 55% PCR blend to simulate variation around that 50% target. Using the rule of mixtures, we were then able to predict the properties of these blends, and as they were expected to pass industry standards across the board, we moved forward with our blend fabrication. Thanks to the Moore Lab in the chemistry department at Virginia Tech, we were able to gain access to a Lystritz ZSE 18 co-rotating twin screw extruder with a 40:1 L/D ratio. Using this, we fabricated 3 1-kilogram batches with those varying PCR contents. One of those batches can be seen here on the left, with the top white layer being our virgin polymer, the center gray layer being our PCR, and the bottom black layer being our carbon black master batch, which contained carbon black, our antioxidant package, and then some virgin polymer to help with the compounding. In the center, you can see our polymer being extruded through a water bath to cool towards our pelletizer, which then pelletized our samples for the final product on our right. Following this, we move forward with testing our final blends, which as you can see, performed very well, passing almost all industry standards. Of note, our final PCR contents were 41.9, 46.5, and 51.2%. This is slightly lower than what we blended in at, but this makes sense as this is due to the carbon black master batch which was added, as that contains some virgin polymer as well to help with compounding. For OIT, which had an industry standard of 20 minutes, we see that we were able to almost double industry standard for all of our blends. And again, if we wanted to increase this further, we could simply add slightly more antioxidants. For ESCR, which has an industry standard of 48 hours, with a type A tensile bar, a type A ESCR tab, which again is more strenuous than is what actually required, as only type B is required for this, we were still able to significantly pass the industry standards, surpassing it by 5 times for our 41.9% and almost 5 times in our 46.5% PCR blend. Testing was not performed on the 51.2% PCR blend during this semester due to time constraints. For melt flow, which does not have an industry standard, these values were deemed to be close enough to that of the virgin polymers that it was considered a success. For carbon black percentage, this is the one category where we did face some issues. We slightly overshot the top end range of 3%, which is allowable. We, however, believe that there's more of a reflection of our inexperience with the compounding and blending process than it is reflective of the blend that we chose. We aim to compound in at 2.75%, however, slightly overshot this. We do not believe this is something that the Prysmian group would have issues with on their lines. Next, as ESCR was deemed to be one of the more important and critical properties, more testing was performed after the end of the semester. Testing was performed on both the Type A, more strenuous, and the Type B, less strenuous tabs, with the Type B being what it would actually be compared to for industry standards. As we can see, no matter which set of results you look at, we were able to pass the 48-hour threshold for all of our tests. Specifically looking at the Type B sample, which is what it would be compared against, we see that the 41.9 and the 46.5% PCR samples were able to surpass more than 1,000 hours with 0 failures, and that our 51.2% sample was able to surpass 528 hours with 0 failures, again, more than 10 times the industry standard. Of note, we see that ESCR does appear to be the most sensitive physical property impacted by PCR content, with seeing a significant decrease in performance after we surpass that 50% PCR threshold. This confirms to us that it is one of the more important properties to plan around and design for when creating these sustainable blends. Next, we also perform mechanical testing, and again, across the board, we're able to pass industry standards. For yield stress, which had a industry standard of 8.3 megapascals, we see that we're able to more than double industry standards for all of our blends. For percent elongation, which has an industry standard of 400%, we were similarly able to more than double industry standards for all of our blends. Of note here too, those pluses signify that for each of those blends, at least one sample was able to max out the tensile testing equipment available to us, as can be seen in the image on the bottom, with one of our initial untested tensile bars next to one of our tensile bars, which was able to max out the equipment and did not fracture. Finally, after aging for 14 days, which is twice the industry standard of 7 days, the samples were retested, and as we can see, they all retained at least 75% of the original performance, meaning that they pass industry standards for that as well. Finally, we recharacterized the variability of our final blends to compare them to both the virgin and the PCR blends from the initial. And as we can see, our variation was able to be significantly decreased through this blend making, decreasing from those values between 30 and 65%, which we saw in the high PCR content blends, down to between 1 and 10% for most of our tests, with one outlier at 15%. Making these polymers these blends significantly more useful. Finally, in conclusion, we were able to fabricate sustainable blends which contain circular material content. These blends were able to pass industry standards and had properties comparable to the benchmark materials widely used in telecom cable applications already. ESCR performance does appear to be the most sensitive to PCR content in blends, and as such is the most, for us, the most important property to design around. And then finally, ongoing work includes scale up of these sustainable blends by the Prysmian group so that hopefully they can be industrialized and released. We would like to acknowledge all of the different groups that helped us be able to perform this research, the Prysmian group for providing us access to their labs and funding this project, and Dr. Brian Risch for being our industry advisor and helping us throughout, the Virginia Tech Department of Material Science and Engineering for hosting this project and the senior capstone, Dr. Gary Pickrell for being our faculty advisor, and Dr. Tom Staley and Professor Christine Burgoyne for helping organize, again, the senior capstone. And then finally, the chemistry department for allowing us access to their labs to perform our testing. Thank you very much.
Vincenzo, thank you so much for this great work. Obviously very relevant as we all move towards a more sustainable future and a circular economy for all materials. If anyone in our audience has questions for Vincenzo, please enter them in the chat, and we'll ask Vincenzo in the remaining minutes of our webinar. But one question that came up was, have you discussed either with Prysmian or within your own colleagues at Virginia Tech the impact of materials that contain ingredients such as flame retardants or other components rather than just virgin polyethylene based polymers? So, and would the effects of recycled content affect them in different ways, whether it be mechanical or other performance issues?
So while we didn't check specifically for flame retardants, the PCR that was provided to us did have contaminants in it. So when we did do some FTIR characterization, we saw hints of some polypropylene and other forms of contaminants, and that is something that you do have to work around, and why they weren't good enough to just be standalone polymers. But in terms of specifically checking for how specific contaminants affected it, that wasn't within the scope of this. But we did see that even with levels of contamination, which were able to show up in FTIR through blending with virgin polymer, we were still able to overcome this and make a usable product.
Would circular or returned content, recycled content, what have you, if it has more flame retardant in it or other ingredients, would that impact certain performance criteria, whether again mechanical or physical?
I don't have as much experience working with those kind of additives, so I don't know how they affect material properties, but I expect
Right.
that it would have an effect, yes, that you would have to work around.
Sure. So it's really kind of lining up, I guess, the recycled content to specific products and specific applications. You have to kind of marry up, I guess, the feed streams of a
That
product
would definitely be
return.
useful.
Yeah.
Hmm.
Um, and I guess you may not be able to address this from a larger standpoint. And I know Brian's in the background. Maybe Brian knows, but um, obviously, declarations of recycled content is good to do, and I'm wondering if one of the questions that came in is are any kind of industry regulations or even customer demands saying, hey, we would like to see a certain amount of circularity and recycled content. Is this going to happen over time where the demand is going to be increased for sustainable products?
Hmm. So that might be something that Dr. Risch can comment on more, as he's been in industry for longer. But from my understanding, there are, especially from the European side, um, a larger push for this and potentially even incoming regulations. But that might be something that Dr. Risch can comment on more.
Yeah, I think, Vincenzo, you've seen, from the automotive standpoint that, definitely, and, being with Volvo, they're a leader. And, within wire and cable, we're not seeing anything industry wide, but certainly we're seeing more and more of the customers asking about sustainability, especially in Europe. But we're actually seeing US customers asking about this. And, there is some language in some of the US specifications that does allow, wiggle room for recycled content. I think there eventually, is some room to further specify, to guard against making a mistake, maybe trying to put too much recycled content in it. As Vincenzo showed, you can, get to a point where you might see a trade-off in properties. If you have a cable that only lasts for 5 years, it's not very sustainable. So you still want to have the long lifetime and then minimize the carbon footprint through best practices, sustainable supply, circular supply, and as well as design, using less materials in the cable. So Prysmian's using all of these methodologies to minimize our impact. And it's something, we're seeing a pull from the customer as well. The standard, industry standards, they're probably going to be the last to change, but it's driven by the customers at this point.
Yeah. Vincenzo, you're working for a really fine company in Volvo that are always looking for improved safety, performance of the vehicles, an outstanding company. Do you see them, Volvo, actually demanding of your suppliers of materials and components of vehicles, trucks, or what have you,
Mhm.
demanding these kinds of materials, but obviously not compromising, physical attributes and other performance attributes?
Absolutely. Yeah, absolutely. So that's actually a large part of what I do in my current role is we look for more sustainable applications. So we have a targeted percentage of recycled content that we want to have in our trucks. And we're working towards that right now. So absolutely, we're not able to obviously compromise the performance. So it is a lot of designing around that. And similar to this project here is how can you work with those properties and you're not using necessarily 100% recycled content, but absolutely, we're already working on getting more and more of that in our truck. So there is
And
definitely
another,
demand from that side.
that's fantastic. And again, if you make comparisons to aerospace or automotive, the lighter the better, and again,
Absolutely.
just for any kind of efficiencies. But an additional question is on applications, and again, let's maybe wiring cable is a specific application. Do you find that the recycled content from a more generic circular return, from many applications can be applied to wiring cable, or do we have to bring back specific materials that have been recovered from, say, wiring cable that have been removed from applications and recycled? What's the cross pollination from different applications into wiring cable?
So I don't necessarily see a need to specifically pull from wire and cable waste. I think there could be potential benefits from that if you know that it's coming from wire and cable and you know that there's certain additives that you want. So one of the things we did OIT testing initially for our PCR content to see if there was any residual antioxidants in our product. So if we had seen that it already had decent resistance to oxidation, we may not have needed to add as much antioxidant. Similarly, if you have a product which already has carbon black in it, for example, or maybe flame retardant, I don't know if there's ways to characterize for that, but we were able to during running TGA, we also tried to check if there's any carbon black in those samples we'd gotten in. So it may allow you a little bit of ease on that processing side, but you would still have to verify. But I believe you should be able to use various feed streams. You just have to be careful with any additives that might be in there already from its past use case.
And again, this may be a question back to Brian. Are there specifications and requirements that you have to create for your suppliers of this recycled materials? Just again, to make sure that they don't contain ingredients or they don't have certain parameters that won't be easily extrudable. I mean, what kind of specifications and requirements are you going to be putting on suppliers of recycled content?
That's a really good question, Dave. And it's something, basically we want to have a sustainable product, but as I said, the product isn't sustainable if it's not durable, right? So part of our environmental product declarations talks about product lifetime. So we really want to have a product that's a 30 or a 50-year lifetime product, which is based on things like antioxidant content. So we need to, even with these recycled materials, we need to have some sort of an incoming specification to monitor things like viscosity, foreign metal content, things like that, other types of contaminants. So you have threshold levels, as Vincenzo mentioned, we can have a certain amount of a small level of contaminant and not have any problems at all, but you do need to work with your suppliers and have some kind of control. So that's something, you either need to move that down the supply chain or control it yourself. So typically we will work with the suppliers of the recycled material and have some kind of a specification. It could be pre-blended or just the recycled material, but there has to be some quality control, so this isn't like making lawn furniture or something like that, where the
Right.
leg breaks off, you throw it in the trash. And really, that's not very sustainable. But really, we've got, our product should last 50 years. I've done a bunch of, lifetime studies of products, and we design our products to be 50-year products. And, we've published some papers on that as well. And in order to do that, you have to control all of your raw materials, including the circular raw materials.
Right. Well, I see no more questions in the chat, so we certainly want to thank Vincenzo for, again, a very comprehensive study of product circularity, recycled content, and the effects on extrusion and performance, and all the requirements that we need for both safety and performance. So again, thank you, Vincenzo. And again, please note the contact points where you can reach out to either Vincenzo or Brian at Prysmian, and they'd be, I'm sure, happy to respond to any questions that you might have. Again, each of these webinar events are recorded and are archived on our IWCS website. So normally takes up to a week or so to have them up on the website. So please feel free to share this with your colleagues. And I invite you to go to our website, and you'll see a whole variety of webinars that we have posted there that date back now for almost 9 years of presentations that are still very relevant and will lead us into the future. Our IWCS webinar series conducts webinars once or twice a month. And our next scheduled webinar will be on Tuesday, December 3rd. And then we will subsequently have a second webinar on Friday, December 13th. So each of you will be receiving notifications and announcements of these events. So please feel free to share these announcements with your colleagues so that they can join us as well. It's important that we recognize our sponsors, our partner level sponsors specifically for IWCS, and they contribute greatly to the success of our Cable and Connectivity Industry Forum. And without their strong leadership, their content, but also their generosity financially, we would not be able to bring these important technical innovations and information to you and our global community. So again, we thank Prysmian, who is one of our partner level sponsors, as well as the other leading sponsors in our industry and suppliers for your support. For over 73 years now, IWCS has been the recognized leader in showcasing new technologies and processes and applications for cable and connectivity. And our next 74th annual Cable and Connectivity Industry Forum will take place Monday through Thursday, October 27th through the 30th in Pittsburgh, Pennsylvania, USA. So please watch your inbox. So we're beginning to put together the concepts for the conference to build on the success of this year, and the actual call for papers, looking for each of you to present your work and bring recognition to both yourself and your company at the event in Pittsburgh. So be on the lookout for the call for papers. Very simple process to submit your abstract for consideration. So again, we thank Vincenzo, and we wish you all a great weekend. All the very best. Thank you.